Hi, welcome to Statics 1. We're going to do a quick review of some of the basic concepts of physics, particularly Newtonian physics, that you need to have a good understanding of to succeed in this class. So the two basic concepts are relation between mass and gravitational force or weight force. And you also need to have a good grasp of Newtonian laws of motion. And you recall, of course, that there are three laws. So we're going to go over those today. So first of all, let's talk about mass and weight force. So if we have an object, I'm going to draw a box. Okay, and based on the number of atoms in that box and the atomic weight, it's going to have a particular mass associated with it. Let's say it's 1 kilogram. So mass equals 1 kilogram. We take that object, take this box to the moon. We take the box to Mars, Jupiter, anywhere within the universe, it's always going to have the same mass. It's an intrinsic property of the object. It's unrelated to the gravitational force applied on it. However, if we were looking at the gravitational force between this box and any other box, or let's say we have a circle here, and there's some distance between them, which we'll call r, the gravitational force between these objects is simply going to be force, that's gravitational force, times some gravitational constant, we'll talk about that, it's a very small number, times the mass of our first object, the product of the two masses, and then we're going to divide it by the distance squared. Okay, and that's essentially the force between those objects. If I hold these two objects up, is there a gravitational force between them? Yes. Can I feel it? No, I can't, because the mass, this gravitational constant, is so small that the gravitational force is basically not something that we can actually feel. However, basically, for something like a planet, like if this mass were to be the mass of planet Earth, and we look at the radius between the center of the Earth and our object, we're going to find that we do end up with appreciable force that we can feel, and that's why we don't obviously float up in the air. I'm sure you've heard this many times. So I'm going to draw planet Earth. Where will I put it? Where will it be on the screen? I'm going to move the screen over a little bit. Let's try this. Which way do I go? This way. All right. Here's our planet Earth. And here I am. I'm actually jumped up in the air. And I'm up here. And there is, in fact, a gravitational force. We don't want to see if this is visible. Yes, it is. There's going to be a gravitational force applied from the Earth on me. It's going to be downward and in the direction of the center of our planet. And basically, it doesn't really matter. The magnitude of that force doesn't matter if I'm here or if I'm here. If I put my alternative me somewhere else on the planet, it's also going to have a gravitational force. And these are basically going to be approximately the same because the Earth is more or less a sphere. For very precise calculations, in fact, it'll be slightly different. But we can essentially take these three terms, the gravitational constant times the mass of the Earth, divided by the distance, the radius of the planet, and we can come up with essentially a constant, which you should know equals 9.8067. Now we're talking about in SI, or metric units. 9.8067 meters per second squared times the mass 2. That's my mass, the mass of our box or whatever it is sitting on the planet. So I'll just call that mass 2. Okay, so that's going to be the gravitational force. And you should know that the dimensions, for example, of a force would be like, the dimension of the force is force. You would have units of either like pounds or newtons. pounds will be like in US units, newtons would be in SI units. This is an acceleration, and this is a mass, and of course mass would be either in SI units, well, it's a mass, or the dimensions. But the units would be in, for example, kilograms, or it might be in pound mass units. Excuse me, if it's in pound mass, we'd have a different constant. So let's live in our SI world for now. All right, so that's gravitational force. And keep in mind, and we'll talk about this in a minute when we talk about Newton's laws of motion, the Earth is applying a force, a downward force, towards the center on the person sitting here. However, this person or the object, if I put a box here, it'd be the same concept, but the object is in fact creating a force on the planet towards that object. Okay, but however, the mass of the Earth is so large that this force is basically de minimis. In other words, it's small enough that we don't really have to think about it. For the most part, so that's it. So that's the gravitational relation between gravitational force and mass. Now I'm going to pause the video, erase the board, and then we'll talk about Newton's 3 laws. Now we're going to talk about Newton's laws of motions, which basically describe what happens to an object when you apply a force to it. All right, so these are Newton's laws of motion. And these are from the 1700s. They've made basically observations based that we're still basically are using to this day. All right, so what is the first law of Newton's laws of motion? It's that if you have a particle, so we'll just talk about particles for now, and it's moving either at a constant velocity or it's at rest. At rest. At rest meaning it's not moving, right? So we have this particle, either it's moving at a constant velocity or we have this particle at rest. They're going to tend to stay at either at that constant velocity or at rest unless you apply some force to it. So particles at rest, meaning they're not moving, or at constant velocity. I'll just write short term, stay that way. Although we know, stay that way. We know that we're really talking about they stay that way unless we apply some other force to them. And it's important to understand that these are what we call equilibrium conditions. In other words, they reach some conditions that they like, and they're going to stay in those conditions basically forever, unless some opposing force is applied to them. All right, so the second of Newton's laws of motion is that, I'm reading my notes here. When you apply a force to an object, it's basically if you push a box, let's say, it's going to accelerate, right? You're going to basically moving it at a particular acceleration. That acceleration is inversely proportional to the mass of the object. All right, so we'll just say this in short terms, which is that the force, your applied force, results in an acceleration, but it's times the mass. And I like writing it in a little bit different way, which is that acceleration equals the force divided by the mass. So the acceleration is proportional to the force and inversely proportional to the mass of the object. So we're talking about some object, we apply a force, F, and that causes some acceleration. Put M here for mass, and it results in some acceleration of that object. Remember acceleration, the units in SI units, let's say, is always going to be mass divided by seconds squared. Keep that in mind. Frequently, there is confusion among many students. And the force, if we're dealing with SI units, is going to be in newtons. All right? And the mass would be typically in kilograms. That's in SI units. All right. The third of Newton's laws of motion is that for every force, there's always going to be an equal and opposite force. For every force, there's going to be a force of equal magnitude in the opposite direction. So if, for example, I lost my planet Earth. Can I fit it in over here? Okay, here's my planet Earth. And we have an object sitting on it. I'll put it actually up here in the air. And you remember that the Earth applies a gravitational force towards its center on the object. And in fact, the object is applying an equal and opposite force in the other direction. I'll do it in green. On the planet Earth. Okay, so this is just an example of our Newton's laws of motion. The third law of motion, and I'll write it out here, which is that there's for every force, let's say it this way, equal opposing force. Get rid of equal. So for every force applied to an object, there's always going to be an equal opposing force applied in the other direction. So let me give you one more example. If we have a beam and we have some supports, and I'm going to use sort of typical symbols. This is, where am I? Well, let me move our screen. I'm off screen. All right. So here I am. Here's my beam. Basically, you may have like a person walking across the beam, and he's applying downward force. This is called a support, and it's basically a type of support called a hinge. We'll be talking about that more later. In this case, we'll put a roller down on this side. And if I were to kind of separate these to show the forces, just like I did up here, what we'd see is that, and I'm going to put my hinge here with kind of a gap in between. Understand it's just done for sort of demonstrative purposes. But in this case, what we realize is that the beam is applying a force on our supports. And the supports will be applying a equal and opposite reaction response, we call that. That is going to be in the other direction, that's holding up the beam. Okay, so this is another example of Newton's third law of motion. Okay, is that we're going to have the beam acting downward on the supports, and the supports, by virtue of our third law of motion, we know to be applying an equal and opposite force upward that's going to keep the beam from basically floating down into the ground. Okay, so that's our quick review of physics. We talked about the relation between mass and gravity, and we talked about Newton's three laws of motion, first of which is that particles at rest or at constant velocity, in other words, at their equilibrium conditions, will stay that way unless there's some unbalanced force applied. We know that the force applied to an object will cause that object to accelerate, proportion to the force and inversely proportion to the mass of the object. And the third law of motion is that for every force, there's going to be an equal opposing force applied back to it. So these are the basic review. Make sure if there's something you're a little fuzzy about, to go back and look at your old physics textbook on other sources to help clarify these basic concepts. So next we're going to move on to other good things. I don't know exactly what, but I'll see you in class.